just have two goals for today, and they're fairly simple goals. And they are to get a power rule for derivatives and to get the quotient rule for derivatives. And we shall top off the day with a song. So our goal is to prove this guy right here. And we're going to do it in two stages. First of all, we're going to prove it for for non-negative ends. And then we're going to, that are integers. And then we're going to prove it for negative ends that are also integers. And then sometime in the future, we're going to prove it for rational ends, that is, ends that are can be written as fractions or ratios. And then finally, much farther in the future, we will prove it for all real ends. And then our second goal is to prove the quotient rule. Which, as you all recall from the famous song that runs through your brains when you're lying awake in bed at night, it is low D high, less high D low, all over denominator squared. And this is probably the most involved derivative rule that we have on here. Meaning that you would not want to remember the form without the aid of a song. And we can take these in any order. So, what's your preference? Quotient rule or power rule first? Power rule. Okay, fantastic. To get to the power rule, we remember that we were stalled out on a question. And the question was that if f of x is equal to x to the n, then f prime is going to be the limit as h goes to 0 of x plus h to the n minus x to the n, and all of that over h. Now, because we've got n's and h's, I'm going to have to be careful. So these are n's, and these are h's. Okay. And the problem that we had was what to do with this. And so, over the weekend, I asked you to read something that seemed kind of irrelevant. Did you guys all find and read the combinations and permutations document?
Yes, I found it very irrelevant.
You found it very irrelevant, but it's going to actually become very relevant. Did you get a chance to read it? Okay, do that because you're going to need it for what we've got going on here. We're going to expand x plus h to the n according to the binomial theorem. And here's what I claim. This is an algebra theorem, not really a calculus theorem. X plus h to the n can be written as, if you'd like to move where you can see that. In fact, John, the seat in front of John is unoccupied because he didn't fully follow directions.
Isn't that Tennessee or just?
It's Tennessee. Okay. What I claim is that this guy right here can be written as the sum of n plus 1 terms containing powers of x and h whose exponents add up in all cases to n, and whose coefficients are the choose numbers or the combination numbers in choose k. Now let me write this in compact form using sum notation. In other words, what we're saying is that x plus h to the n is the sum starting at k equals 0 and going all the way up to n of n choose k times x to the power of n minus k times h to the k power. Now let me do a couple of examples first, and then I'm going to come back and prove the binomial theorem in a delightfully easy way. So for example, let's say I have x plus 5 to the, let's do the second power since we can check that one. That according to good old FOIL, which is really just distributive property, this would be equal to x squared plus 5x plus 5x plus 5 squared. And if I write it in terms of the binomial theorem, that would be the same as n choose 0, which is 1, times x to the 2 minus 0, which is 2, times h to the 0, which is invisible, plus 2 choose 1, which is 2, times x to the 2 minus 1, which is 1, times 5 to the first power, plus 2 choose 2, times x to the 0 power, times 5 to the second power. 2 choose 0 is 2 factorial over 2 factorial times 0 factorial, which is just 1. And so I get x squared for my first term. 2 choose 1 is 2 factorial over 1 factorial, 1 factorial, which is 2. So I get 2 times 5, which is 10, times x. And 2 choose 2 is automatically the same as 2 choose 0, which is 1. So that I get 25 as advertised. Now, for the really small exponent 2, appealing to the binomial theorem is not nearly as efficient as just multiplying it out, right? So we look at that and we go, okay, that's not a great savings to us. But what if I wanted, let's say x plus 5 to the 17th power, and I want to know, find the fourth term of this expression. In other words, when I multiply it out, I'm going to get x to the 17th plus something x to the 16th plus something x to the 15th plus something x to the 14th, and that's my fourth term, and I want to know what is the coefficient of that fourth term. So using the binomial theorem, I can come back here and I can identify that the fourth term, remember that we're starting counting at 0, is going to be 17 choose 3 times x to the 17 minus 3, or 14, times 5 to the 3. Notice that they add up, the exponents add up to 17, which is the same as 17 factorial over 3 factorial, 14 factorial, times x to the 14 times 125. And when we simplify 17 factorial over 14 factorial, we get 17 from 16 times 15 over 3 times 2, which is 125x to the 14. And let's see here, that gives us 8, that gives us 5, so we have 40 times 17 times 125. And I hope you'll forgive me if I don't feel like simplifying that at this time. But this would be our fourth term of that expansion. And the whole expansion would have 18 total terms. How are we doing so far? Have you seen binomial theorem before? Or is this first term? We have seen it. Last year we talked about it a little bit. Okay, yeah. We probably talked about it in terms of Pascal's triangle. Did we do that? The Pascal's triangle? The Pascal's triangle relies on a nifty property of the end of the choose numbers right here.
Oh, yes.
6, 4, 1, here. And if I were to pick out one of these coefficients right here, then I would identify it as n equals 4 and 0, 1, and k equals 3. So 4 is equal to 4 choose 3. And the way that Pascal's triangle works is it relies on the property that 4 choose 3 is the same as 3 choose 2 plus 3 choose 3. And this was the theorem that is found in your handout. And actually, let me go over the proof of that for just a moment. 4 choose 3 chooses is the number of ways that I can choose 3 items out of a set of 4. So if I have 4 people here and I'm going to choose a delegation of 3 of you, then there are 4 different ways to do that. And actually the easiest way to see it is if I choose 3 of you, then there's 1 person left out, right? And so I can choose 1 person out of the 4 of you to be left out. There are 4 different committees that I can choose. That's the easiest way to see it. So, if I'm going to choose a committee of 3 people, then let's pick 1 person and identify Charlie. He's going to be a person, right? And we can now count the total possible committees of 3 and 4 by considering the committees that have Charlie in them. If Charlie is going to be in a committee, then that leaves 3 of you, and I'm going to pick 2 together with Charlie. So that would be 3 choose 2. And then we can consider the committees that do not have Charlie in them. If we exclude Charlie, he's the guy left out, and that leaves us choosing 3 out of 3. In other words, it's going to be you 3, and that's it. So, the total number of committees we can pick is the total number of committees with Charlie plus the total number of committees without Charlie, and that is Pascal's identity for the choosing rules. Does that make sense to everybody? Okay. So, coming back to this binomial theorem, we now have an expression for this, and because we have an expression, what we can do is to write our difficult x plus h to the n in terms of the binomial theorem. Let me copy it down. Group this. Copy it. And put it on a new page. Paste it. There we go. And let's keep on going, writing out x plus h to the n in terms of the binomial theorem. That's going to give us x to the n plus n choose 1, x to the n minus 1 h, plus n choose 2, x to the n minus 2 h squared, plus a whole bunch of terms follow. We end up with a total of n plus 1 terms, and our last one is h to the n. All of this I should probably have written in blue because it corresponds to the blue circle there. And then we're going to subtract off the x to the n that we had here and divide by h. And again, I'm getting sloppy with my n's and h's. This guy is n, and this guy is an h. That's n. And that is H. Okay. This is the key move in the proof. So if there's any question about how this is working so far, then let me know. No questions. Great. So the next observation is that my x to the n's, boom, boom, cancel. now I'm left with a whole bunch of terms that all have a common factor of h. So I'm going to factor that factor out, leaving me with n choose 1 times x to the n minus 1 plus n choose 2 x to the n minus 2 h plus all the way down to h to the n minus 1. And all of that is divided by h. Well, first thing is first, we cancel a factor of h. And now we let h go to 0. This is too close to the other end. So let me pull that down so that it's not interfering. Give you a second to catch up. And we observe the key thing. Now that the factor of h is canceled, when I let h go to 0, glorious zeroings occur. This term goes to 0.
Oh.
Come at me, bro. This term goes to 0. All these terms in here have some power of h, and they go away. And the last term has a power of h. And what's left is just n choose 1 times x to the n minus 1. But what is n choose 1? First, think about it in terms of combinations. N choose 1 is the number of ways to choose one element out of a set of n. That's clearly n. Or think about it computationally. It's going to be n factorial over n minus 1 factorial times 1 factorial. And n factorial over n minus 1 factorial cancels all these factors except for the factor of n. And there we go. That's it. This proof of the binomial theorem is one that students should be able to do. Excuse me, this proof of power is one that students should be able to do. And because the key move relies on the binomial theorem, you'll have to actually know the binomial theorem to do it. But the best way to know things is to know why they're true. So let's come back to the binomial theorem and ask, why is the binomial theorem true? And I'm just going to write this in compact form because we're going to see this a whole lot with regard to we're going to see this notation a whole lot with regard to polynomials come February. Here's why this is true. Let's take and expand this according to what it means. X plus h to the n means multiplying x plus h times itself n times. Okay. Now, when we do this, we recognize that this multiplication is a serious pain in the neck, right? Because I'm going to have to multiply x plus h times x plus h. And then I'm going to have to multiply that times x plus h. And then multiply that times x plus h, and so on. So if I wanted to do it in that way, it would be horrendously inefficient. And I don't think I've seen any really good patterns on it. Instead, here's what I'd like to do. I'm going to observe that the way that the multiplication happens is that you are distributing first this one, and then this one to there, this one, and then this one to there, taking the results of that and distributing and distributing and distributing and so on. Okay? And the distribution process ultimately is going to give you a total of 2 to the n terms And each term, some of those terms will combine together, right? But if I leave them uncombined, you have 2 to the n terms. And each term is going to have one of these two multiplied by one of these two multiplied by one of those two, ultimately all the way down to one of those two. In other words, I'm going to have a power of either x plus h out of each factor, and that will give me that particular term. Ultimately, I'm going to have to combine these, right? Okay. So for each term, we have, let's just say we have k powers of h. And if we have k powers of h, then we will have n minus k powers of x. Does that make sense what I'm saying, or should I do a concrete example? Do an example? Sure. So if I had, for example, x plus 2 cubed, like so, then that would give me x times x times x plus x times x times 2 plus x times 2 times x plus x times 2 times 2. In some ways, this seems like a slow way to do it, but there's going to be a benefit in just a minute. Plus, now that's the 4 terms that start with x. Now we do the 4 terms that start with 2. It's going to be 2 times x plus 2 times x times 2 plus 2 times 2 times x plus 2 times 2 times 2. And so I get all 8 terms right here, 2 to the third, and each one of them has one choice from here times one choice from here times one choice from there. Does that make sense? Good. Now, if we now combine like terms, we can see that some of these terms are alike. We've got these two alike. Now I screwed up. Hang on. x2, x2x. No, I didn't screw up. Here we go. 1, 2, 3 there. And we have 1, 2, 3 like terms there. Okay? Now, why did we have 3? We had 3 because there were 3 different ways that I could choose 2 x's and a 2 out of my set of 3 x plus 2's. And there were 3 different ways that I could choose 2 2's and an x out of my set of 3 different 2's. But there was only one way I could choose x, x, and x. And there was only one way that I could choose x, 2, 2, and 2.
So you need that x and u h k that you wrote in each terms.
Yes, exactly. That's right. So here, my k, for this term, my k is 1, and my n minus k is therefore 2. Good. So if I were to use that logic to write this out, I would say that there are 3 choose 0 ways to choose 0 factors of h out of 3 factors. And there are 3 choose 1 ways to choose 1 factor of 2 out of 3 factors. And there are 3 choose 2 ways to choose 2 factors of 2 out of 3 factors. And there are 3 choose 3 ways to choose 3 factors of 2 out of 3 factors. And 3 choose 0 is 1. And 3 choose 1 is 3. And 3 choose 2 is 3. And 3 choose 3 is 1. And of course that all simplifies. So coming back here, I'm just going to make a simple argument that I think you can follow from the example. And that is that for each term we have x to the n minus k and h to the k. And now, how many different ways can I choose k factors of h out of these n factors? Answer. N choose k. Boom. John's not so sure. Pretty good. You're more awake than you were Friday. So you should. I see progress. So because there are n choose k ways to choose k factors from n. All right. I'm going to do quotient rule. If we have time, I'm going to do a second proof of the power rule that does not rely on binomial theorem at all. If we don't have time, I'll put that into a video and put it out. Should be 7 minutes, something like that. The proof of the quotient rule is not like the proof of the power rule. The proof of the power rule relied upon this binomial theorem that was new and sort of weird looking, but in the end it wasn't too hard, right? You set up the limit, you expand it with binomial theorem, and then you do what comes naturally. The proof of the quotient rule is easy. You set up the limit conceptually, but then you have to do a clever subtract and add thing, and then you have to do a lot of messing out with it. So there it is. It's more like the product. So here it is. My theorem is that the derivative of f over g is that thing. And so we'll set it up with limit definition. Blah. It's funny, I haven't thought about that in a while, but that saying came from a sophomore year English teacher who ultimately got fired because he cussed out the headmaster. It was not a good plan.
What's that?
What's that? Boo. Okay, so we're going to do what comes naturally here, which is to get a common denominator. And to do that, of course, that means g of x here, g of x plus h, g of x plus h here. And so on the top, I get f of x plus h times g of x minus f of x, g of x plus h. On the bottom, I get g of x plus h. And now, just to keep my head straight, I'm going to rewrite the division as multiplying by the reciprocal for just a minute. Just so that it doesn't get too vertical. I hate really tall vertical stuff. Even in New York City, I don't enjoy it because it's proportioned differently than other cities. Straight up. Okay, so now we're going to pull off a couple of things. First of all, I'm going to appeal to the commutative property of multiplication to switch the order in which I multiply, because what I really want is the h down in the bottom. The second thing that I'm going to do is I'm going to subtract and add the same thing. So I better give myself some room to do that. And you remember that the spirit of subtracting and adding was that what we were trying to do is to allow us to factor pieces. And the piece that I want to pull out of here is going to be f of x plus h minus f of x. So clearly I'm going to need to have minus f of x as the first part of my term, and then times g of x as the common factor that I'm going to pull out. And if I subtract that, then I have to add f of x, g of x here, so that I'm not changing the value. And we just hope that's going to work out in the second pair of terms, and it will. Does everybody see the logic of that? I kind of know ahead of time what it was that you wanted to subtract from that. And now we're going to do several steps at once because you guys have seen this enough. We're going to rewrite this as g of x times all over h. And we're going to write this as, well actually let me leave the algebra part alone. F of x times g of x minus g of x plus h all over h. And so here I did the splitting and the factoring, all of the algebra stuff at once. Yes, thank you. So that's the algebra. Now let me do the calculus part. When I do the calculus part, then I'm going to first of all do product rule for limits. Just like that. And then second of all, I'm going to do sum rule for limits. That. And all of this, as Catherine sagely observed, is still multiplied there. Okay, let's go through one at a time. Keep in mind that x is not our variable, h is our variable, h is going to 0. So g of x is just a constant. Out it comes, we take the limit, and lo and behold, f prime. F of x likewise is just a constant, so out it comes. Wait a second, what is the limit as h goes to 0 of g of x minus g of x plus h all over h? No! Bingo. It is the opposite of g prime. I think you got fooled by finding a 0 in the top and not checking the denominator. Don't be in such a hurry. Now, what about our second factor here? Our second factor is the limit as h goes to 0 of 1 over g of x plus h. So 1 over g of x again comes out, h goes to 0, and I get simply g of x. So that the whole thing goes to g of x squared, like so. Put it all together, what do you get? G times f prime minus f times g prime all over g squared. Ta-da! It's just a big algebraic workout. And it's good for you like nothing. Okay, I think we should do the song because, hey. How you doing? Fine, I guess. Okay. Now this song is not original to me, but my friend Lauren Cannell, who was undergrad a little bit later than I was, and now is at APL actually, but I haven't talked to her forever, tipped me off to this song. And you can find various versions on the interwebs, but this is the one I know. If the quotient rule you wish to know, it's literally high, left, high, draw the line down below, and in major squared rule. Now, in order to keep up my standing as cult leader, I have to get people to sing this song. So help me out here, because my accreditation is on the line. You gonna sing? Please wave your arms. Something like that. Here we go. If the Charlie, you got a lead in.
You start and then we'll all join in.
Okay. If the quotient rule you wish to know, it's low, D, high, left, side, below. Draw a line down below. Combination squared rule. Now, as Arlo Guthrie would say, that was terrible. Join Warren stuff, you gotta sing. Feel it. 4-part harmony. I don't think we're gonna do that, but feel it. So, sing it so that Miss Prentice can hear it. Hi, Miss Prentice! Come on, let's go. If the quotient rule you wish to know, it's the highest side below. Draw a line down below. Count it major squared root. That'll do. All right, our time is up. And for that reason, I'm going to do the other proof of the power rule on a video. Just to whet your appetite, I want you to consider doing the derivative of x squared in this way. Suppose I thought about x squared as a product. If I did that, then I would write the derivative of x squared as the first times the derivative of the second plus the second times the derivative of the first, which seems remarkably inefficient, of course, but it has some interesting insight. In that, it reminds me that the product rule is not derivative of one times the derivative of the other. But wait, there's more. Suppose I were to do the same process to x cubed here. And think of x cubed as x times x squared. So that I now can pull in my result from the previous computation, like so, and get 2x squared plus another x squared gives me 3x squared. And now I begin to see something, and that is that if the power rule is true for x for n equals 2, and it is, then the power rule must be true for n equals 3, because I pull in the result right here. And so I wonder if that could happen in general. Maybe let's pretend and assume that the power rule is true for x to the n. What happens if I do the derivative of x to the n plus 1? Well, that would be the derivative of x times x to the n plus 1, which now would give me first times the, x times x to the n. There we go. Which gives me first times the derivative of the second, plus the second times the derivative of the first. And this now, if my power rule happens to be true for x to the n, Then, notice x times x to the n minus 1 is x to the n. Then it also must therefore be true for x to the n plus 1. In other words, if I get a chain going, maybe starting with n equals 2, then if it's true for n equals 2, it has to be true for n equals 3. If it's true for n equals 3, it has to be true for n equals 4. If it's true for n equals 4, it has to be true for n equals 5, and out to infinity like that. That's going to be the spirit of our second proof. And we're going to use the technique called induction. I mentioned in one of our documents previously, the limit properties document. We actually used induction to prove the power rule for limits. Now we'll use induction also to prove the power rule for derivatives. And there will be a couple of other nice little side effects of this particular proof. Questions, comments, or jokes?